Okay, so let's start. This is lecture 20, and today we'll talk about online learning, which is a topic which is different, or at least on the surface, it's very different from what we've been doing so far, except that it connects to the very first lecture on statistical learning that we had on Perceptron, which is an online algorithm. I will try to show a few more connections. There are deep connections between this setting, online learning, and statistical learning. Let me remind you what we did with Perceptron. We proved in a very simple manner a bound on the number of mistakes that Perceptron makes for a sequence of data. And it was a result that held for any sequence of data. It's a very strong result, relied on no assumptions about the data. And then we said, well, let's assume that the data are IID, and let's convert it into a statement about IID data, IID learning. And indeed, with just a few lines, we proved an out-of-sample performance guarantee for the Perceptron, be it one pass over the data or multiple passes until no more mistakes. Right? And it was kind of surprising that you can take this result that holds for an arbitrary sequence and then turn it into what you want. Okay. So today we'll talk about this type of this style of results that hold for arbitrary sequences. And that's a field that we'll call online learning. Sometimes we will make assumptions about the sequences, but mostly the results will hold for all sequences. So why would I want a prediction result that holds for all sequences? Well, suppose that I'm playing rock, paper, scissors. Right? Everyone knows rock, paper, scissors, right? Now, suppose that you play completely at random. You flip a three-sided coin, and then you decide rock, paper, scissors. Then there's nothing I can do, right? That's an equilibrium. I can't really do better than random chance against you. Or let's say we're playing a game of matching pennies. So you decide heads or tails, and I try to match. And if I do match, I win. If I don't match, I lose, right? So that's a binary choice. And if you actually flip a coin, you have a random outcome, then I cannot do anything. But of course, we still play rock, paper, scissors, or penny matching. So what are we trying to do when we play with someone? Well, I'm trying to guess. I'm trying to read your mind, right? When I'm doing this, I'm trying to look at patterns of what you've done before, and try to predict what you will play next, right? So maybe after a rock, you always play rock, right? So I build some kind of mental model or some kind of frequency understanding of what you've been doing in such a situation before. So it's fun, right? It's fun to try to get a bit of an edge and use the fact that the sequence that I'm trying to predict is not random, right? So of course I cannot predict a random sequence, but how can I take advantage of some structure in the sequence? Right? So that's a type of problem that has a long history. I will mention in the 1950s, Hagelbarger, I cannot pronounce his name, and the Bell Labs built a machine, and Claude Shannon, the father of information theory, was there as well, and Claude Shannon also built a machine. I don't know how many of you attended the screening of the Claude Shannon's life just a couple of weeks ago. No, the Lids Symposium. No, okay. Claude Shannon used to build these different toys, machines, and the one to play chess, one to navigate a maze, and this is another machine that he built. So the machine would try to predict what you as a human would enter, and if it predicted correctly, then it would increase the count, and if it didn't predict correctly, it wouldn't. And so the question is, can the machine predict better than 50% chance, right? And of course, if you enter a random sequence, you cannot, the machine cannot do better than 50%, but can the machine kind of understand the patterns in your sequence? And in fact, on an untrained person who would play this machine, the machine would beat the person, do quite a bit better than 50%. So the machine is apparently in the MIT storage facility somewhere in Somerville. So there is a picture of it. I can show you. But so that's a real device. So how would you build such a machine? How would you implement something like that, right? Let's think. So you want to write a program. You're not gonna solder wires, but you'll write a program that will try to learn patterns that I'm entering and predict better than 50%, right? How would you do that? Any ideas? Guesses? What would you try to do? Suppose that's the homework for tomorrow. What do we do? Conditional probabilities. Previous first, right? So the kind of one thing you can try is look at some prefix, and then look at the statistics whether given that prefix, the next one would be 1 or 0. Well, anything else? Any other ideas? What Interesting. If you play randomly, you can't get better than 50%. What if there's seasonality, right? So maybe I'm thinking of a person playing over a course of a year, and when it gets cold, the person produces more zeros, and when it gets warm, the person produces ones, right? Then maybe this type of frequency is not the right thing, but you want to get kind of more global patterns, seasonality into that. Okay, so let's try to formalize this. But before I actually formalize it, let me just stress. So what you could do is you could build a model, a statistical model, assume that the person is generating sequences according to this probabilistic model, P sub theta, and try to understand this theta. Try to learn the parameters and then use the parameters to play the game, right? That's one approach, right? But I'm thinking of situations where it's going to be really hard to model the process generating the data. And also, if I'm modeling the process generating the data as a stochastic process, then what if I'm a bit off in my model? It's not clear that I gracefully, my performance will gracefully decay from being good to, in the misspecified case, being completely off, right? So what I want to do is I want to use this kind of to motivate the setup, which for most of you will be very foreign. But I think if you think a little bit about this, it will start making sense. I will try to get a result for all sequences without assuming anything about their stochastic nature. It's just that my performance will differ. It will not be always good. It will be good if my assumptions about or my hopes are realized. Okay, so let me make this precise. So I'm going to say that there is a sequence y1, y2, yn. I will assume that n is the length, the horizon. You can also consider infinite horizon, typically in a way that, so it's enough to consider finite n, and then you can always double if the problem hasn't finished by n, then you say, okay, my horizon is 2n, 4n, and so forth. So that's not a problem. So let's just fix horizon. This is a sequence of bits that is in plus minus 1. Okay. And I'm trying to predict the sequence in a causal way, in the sense that I will put down a y hat 1 as a prediction of y1. Then I observe y1. Then I make a prediction of y hat 2. Then I observe y2, and so forth. So these are also plus minus 1. Let me write down the protocol. It's a bit easier to write down the protocol because then you know who knows what. So for t from 1 to n, predict y hat t in plus minus 1, and then observe yt also in plus minus 1. Okay? So this is the protocol. And the order of these tells you who knows what, right? So when you make a prediction, you don't know the next yt. And now I also have to tell you whether yt knows the y hat t or not. If yt knows y hat t, there is nothing you can do, right? If the other person playing matching pennies knows what you're predicting, or if the machine cheats and doesn't make it a prediction until you actually enter the bit, then there is nothing you can do, right? So in fact, the second one also shouldn't know about the first one. Okay, and there is a way to do this by saying, well, the first player will actually choose a mixed strategy, a distribution, set it down. The second player can look at that distribution and make a choice based on that distribution. That's a Bernoulli with some bias. But then the actual draw will be realized from that distribution, and yt cannot depend on that draw. Okay, I'll come back to this point in a bit. Let's say that this is the strategy. This is the protocol. And what is it that I care about? What I care about is the number of mistakes. That's easy to write. T from 1 to n. Indicator that y hat t is not equal to yt. Okay? Let's make it an average number of mistakes. Okay? Now, one can see that, okay, so let me go slowly. So what I want, the type of the result that I want is that my performance is upper bounded by some function phi of y1 through yn. And this is some function phi. And I want the result to hold for all sequences, y1 through yn. So for all sequences, I'm not specifying, but they're in plus minus 1. The average number of mistakes I want to be bounded by some function phi, which I will specify shortly. Okay? Now, I want to allow a randomized strategy, as I already mentioned. I will denote the it's a randomized strategy. I'm going to choose y hat t, sample it from a plus minus 1 Bernoulli. Okay, well, Bernoulli is 0, 1, but you can think of it as plus minus 1. I'm going to write it like this: Bernoulli with bias qt. Let's put a hat, qt hat. and this is a plus minus 1 Bernoulli, right? So it's a distribution on plus 1 and minus 1 such that the expected value of y hat t is equal to q hat t. Okay? So for instance, if q hat t is 0, I've got an unbiased plus minus 1. If q hat t is 0.25, then I have my distribution is shifted a little bit towards plus 1 versus minus 1, right? Everyone is clear? Okay, so that's my definition. So I can modify this protocol, give a little bit more precision to what I'm doing. So for t from 1 to n, I pick q hat t in minus 1, 1, right? Because the mean of my distribution has to be between minus 1 and 1, right? If it's exactly plus 1, then it's a deterministic choice of plus 1. If it's minus 1, it's a deterministic choice of minus 1. And then then it doesn't matter. You can say observe y hat t, yt, observe yt, and draw y hat t from. Okay, this is going to be my overloaded notation. I'm going to use q hat t for also for the distribution. Bernoulli with the mean q hat t. Yes. Yeah. So I'm putting plus minus 1 Bernoulli. So it's not a real Bernoulli. It has two choices: plus 1 and minus 1. No, that's the mean. I'm parameterizing instead of probability. You can back out the probability if you want.
So why did you flip them?
I just want to parameterize by the.
No, I mean, why did you flip the observer?
Oh, the order. I just want to make sure that if you think about the order.
Decision, but why do we? Is there a reason why you explicitly?
Why I flip them?
Flip them, yeah.
I can say they happen at the same time if you want. If I flip, I just didn't want you to think that the yt can be based on the actual draw of the y hat t. So it's okay for y.
It shows that both don't know about each other.
Yes, right. That's right. Because I'm just gonna draw, so I can't do anything now.
Yeah.
And this one can depend on the distribution. It turns out to be okay. It's not gonna give more power to nature. It does not give. Yeah, if nature knows the mixed strategy of your play, that does not give more power.
I mean, if the nature can play somehow that cannot better by looking at the bias.
That's right, but my goal is not to. Yeah, so if nature randomizes, if nature is a binary string with no structure, I cannot predict that. My goal is to capture the structure, if it exists, right? That's the goal. So,
So, but it's not okay for y of t to know what q hat of t is. Right?
it turns out to be it's okay, but
Okay,
let
so
me.
the distribution, but not the exact value.
Well, q hat t parameterizes the distribution. It's the mean of the distribution. So that's the same as saying you know the distribution.
No, I mean the distribution of qt itself
Q hat t,
has some distribution to be picked from.
q hat t is a number, is the mean.
Right, but you pick
The y hat t,
distribution, right?
no, I just set that as a number. That's a number. 0.1. That's just the mean.
It is
What-
the
what-
mean of this distribution.
of this
but
distribution.
How do you choose
how do I choose it? Based on the past. Based on the past. I will tell you a prescription for how to choose it. If that protocol is confusing, this is in fact slightly different, because what this is saying is a sequence is fixed a priori. And it turns out not to matter whether it's fixed a priori or it's chosen in that way. But if it's easier for you to think of the sequence as being pre-chosen beforehand, that's okay. That might be easier, just easier to think about. Okay? All right. So what I want is that the average number of mistakes on this sequence, this is my algorithm. Average number of mistakes is bounded by some function of the sequence, because I want to differentiate sequences, and this is where I'm going to put my prior knowledge about which sequences I'm hoping to see, or my, maybe not prior knowledge, but my hopes of what I will see. Let me give you an example. Before that, let me just say that because everything is random now, or I should say my strategy is random, I'm going to write this as an expectation. But it's important to realize that this expectation is not over the sequence. This expectation is over my own randomization, my own draws Q hat T. Right? The sequence is fixed in this setup. In this protocol, you could think of not just observing, but maybe YT is chosen according to the past. Nothing will change. Okay. But you know, you can just think of, oh, I'm observing YT from this fixed sequence, and that's fine. Make sense? Right. So the result that will develop hold for both setups, where the nature is adaptive to what you do, which makes more sense when you're, you know, playing matching pennies because the other person sees what you're doing. But maybe if you're doing if you're investing in the stock market, then maybe you're not affecting what the stock market does. So this is the trajectory of the stock market, and what you're doing has little effect. And then you can think of the nature being not caring about what you do. Right?
So are they assuming y1 to yn are fixed?
So what I'm saying is, maybe I'm stressing this too much, but there are two possibilities, and essentially what we will do holds for the adaptive case, where YT can be chosen based on what I'm doing. But if it simplifies thinking, then let's just say that it's fixed, the sequence is fixed, and you're trying to predict it, right? Which is another way of saying I don't affect the sequence. Right? So think of this as a stock market, has a trajectory. I don't know it. I'm going to try to predict it, but what I'm doing doesn't affect too much the trajectory. Yes.
Why don't we first observe YT and then predict?
Well, if you observe YT, then what is there to predict?
Exactly. So that's why I'm asking. Like, why in the second algorithm first observe YT and then go Y?
Well, think of these as being done at the same time, right? So if you want, right? All I'm doing is I'm going to randomly predict. Okay. So maybe it's time to do an example. So suppose that y1 through yn, now we're going to go back to the classical IID learning. Suppose that y1 through yn are IID Bernoulli plus minus 1 with bias p. Okay, so that's the expected value of the y. Suppose I want to try to predict the sequence. What should I be doing? This is a very strange world where everything is IID. You never get this, right? You just see observations.
Draw Bernoulli's, I mean, that's
So-
the IID you can learn from the past.
Well, but there's a bias, right?
Yeah, and use that P.
So how? But you don't know this,
Oh,
right?
okay. Yeah.
Mm-hmm.
So
Yes. Yeah, so you can do a Bayesian approach where you put some prior on P, and then that's right, and then update it after seeing some data, and then draw from that distribution. That would be one way of doing it. What's another way of doing it? But you don't know P.
so learn P.
Learn P, exactly. So how do you learn P?
The problem is solves to learning P.
So what? How do you learn P? Exactly. You just look at the frequency, right? So the strategy is majority of y1 through yn, t minus 1, right? Right. You just go with the majority of what you've seen, right? So that would be a frequentist analog of what you were suggesting, right? Now, the majority, right? Essentially, what you're asking, the same prediction is, look at the indicator of whether y let's call it y bar t is more than 1/2, where y bar t, or t minus 1 I should say, t minus 1. Y bar t is 1 over s, the indicator that ys is equal to +1, right? So s from 1 to t. So this is a frequency of +1s in the sequence. Yeah? That's now, y hat t is now the frequency of 1s, and 1 minus the y bar t is the frequency of -1s, right? Is that okay?
The problem you need to convert it back to +-1 from the indicator.
So this is a 0-1 indicator, so this frequency is between 0 and 1, and so I'm comparing it to 1/2. So if it is more than 1/2,
Yeah, but the indicator gives you 0 or 1.
oh, you're right. 2 times -1. Yeah, good, thanks. Yeah. Okay, now, so what are we using when you say you learn P? Well, what you're using is the y hat. Sorry, what you're using is that the fact that the y bar t gets closer and closer to P, right? Or okay, not P, not this P. All right, now I have to convert back. So that's a problem. So if P is, so I need to add 1 and divide by 2, is that right? Is that correct? So if P is equal to 0, that's the mean of the ±1, then the frequency is 50-50, right? Yes. Yep. Oh, 1 by t, thank you. Yes, you're right. 1 by t, thank you. Some of these things are easier with ±1s, and some of these things are easier with 0s and 1s. And okay, let's try to think on the spot. Okay, so essentially you are learning the P from the frequency, right? How quickly are you learning? Well, 1 over square root of t, right? The central limit theorem tells you that this gets close to that at the rate of 1 over square root of t. Right? Okay, good. So now, what kind of guarantee do you get? So the guarantee that you get, so I'm continuing the example. The guarantee that we get is that after n steps, y hat t not equal to yt. Now, I'm actually doing deterministic predictions, but it's the sequence that's randomized, right? So I'm going to put the expectation, but this is like a dual of the other problem. Here, the sequence is randomized, right? Now let's do it in high probability. So in high probability, this is a random quantity. This gets closer and closer to which quantity? Well, you cannot. So let's think about this. You can't actually get it to 0, right? Right? You're predicting a source which is, let's say, 70%. Should we switch to zeros and ones? Maybe that will be easier.
Maybe. What was the reason for the negative one?
In the second part of this lecture, it's easier to think of negative 1, 1. How about for, well, no. Oh, that's a problem. All right, let's stick with -1, 1. All right. So if the sequence is 70% bias, right? So 70% of the time you're getting +1, 30% you're getting -1. Now, quickly you learn that the bias is more than 50%. From that point on, you'll be predicting +1. What's the number of mistakes that, what is the proportion of mistakes that you're going to be incurring? 30%, exactly. So one way to write this is it's a minimum of the frequency of zeros and frequency of ones, right? These are the bars. This is the empirical frequency, oh sorry, -1s. Empirical frequency of minus or +1s, and this is -1s. Yeah. So I have the.
Can't you do better than this if you change the strategy? Because I mean, this strategy takes is based on the majority. It based on which one is more likely.
Yeah.
I predicted.
Right. But remember, I'm not predicting the bias. I'm predicting the actual sequence of realizations. So there is irreducible. This is like a Bayes error. I have to incur that Bayes error.
So is this theoretically the best?
Yeah, that's theoretically the best thing you can do. So another way to write this is that this difference goes down as, in fact, 1/√of n, roughly. Order of 1/√of n. And that 1/√of n is because these are random quantities. And of course, what I've written here is a random quantity because the yt's are random. So I would have to say that this is in expectation or in high probability, or almost surely as n goes to infinity and so forth. Okay?
Place perhaps yn4 with bias minimum of n.
Actually, I want to keep it this way. I want to keep it this way. I want to say that what you get from this is, by using a very simple rule, which is just a majority, the frequency of your mistakes goes to the minimum of the frequency of ones and -1s. Yeah? That's the statement. Okay, so the claim, which is very surprising, at least it was to me when I first saw this, is that this result star holds, I'm going to put it in quotes because I didn't specify the probability or an expectation, for an arbitrary sequence without Bernoulli assumption. So what I mean by that is there exists a strategy for the player such that the frequency of the average number of mistakes is close to the minimum of the frequency of -1s and the frequency of +1s, no matter what the sequence is. Okay? Yes, question?
You used the concentration intervals 2 times, right?
Yeah.
For saying that PM 1 minus P is close to this, one for that the left side is close to minimum of PM 1 minus P with the error of 1 over the square.
Yeah, so you need to form some.
I mean,
Yeah. Sure. I mean, one way to do it is to say that I've got my strategy, you form some martingale different sequence, and then just do one concentration. I mean, it's not important. Okay, so let me now try to decode this statement in the context of penny matching. Suppose I'm playing penny matching. What the statement is saying is that I can beat 50% as soon as you enter a sequence that is not balanced. So imagine that you enter a sequence that's 40-60, right? What I'm saying is I can take advantage of that and make sure that I predict the sequence with the error of only 40%, beating the 50% random chance. So I can take advantage of the structure of your sequence, and the structure is imbalanced. So it's not necessarily, what you were suggesting, take a history of 3 and look at 4th, right? This is a global notion which says, if you want to beat me in the game of penny matching, you better be at least entering a balanced sequence, because if you're not, I can take advantage of that. Make sense? Yes?
Should it still be IID variables that you were?
No, so arbitrary sequence. So I will make no assumption. This is where the example ends. And I'm saying that in this setup, I can have exactly the same result for an arbitrary sequence. Okay? So if you're producing a Bernoulli sequence, if I know that you're producing a Bernoulli sequence, you're flipping a coin with bias P. It's easy. I just learn your P, as you were saying, and then go with the majority, or just go with the majority, because majority converges to the max, the 1 or -1, right? What I'm saying is a much stronger result, which says I can get the same as what I would get if I knew that you were playing Bernoulli. I can get the same result without assuming that you're playing Bernoulli, no matter what you play. Another way of saying is, if we're playing penny matching and you want to make sure that you have 50% error, or I incur 50% error, it's better be the case that you give me a sequence which is balanced. Otherwise, I can take advantage of that. Right?
So when you say the claim holds, do you mean for this exact strategy or?
Not for the strategy. So there exists a strategy.
But then there exists a strategy that can even do better than this.
Possibly, if the sequence.
I can give you an alternating 0-1 sequence, and then you can do at
Exactly.
least, I don't know, 75%.
Exactly. So, this exactly gets to the philosophy. I need to collect the things that I believe that I can take advantage of, right? I cannot predict an arbitrary sequence better than 50%, but I can hope that I can take advantage of some patterns in the sequence. So one pattern I can hope to take advantage of is imbalance, and I will show you how. Another pattern could be some seasonality, or what you were saying is even more drastic, alternating, right? Maybe I want to take advantage of 110 because I somehow believe that that might be what you're going to be using, right? So I can collect all these behaviors and I can try to take advantage of all of them at the same time.
So maybe what we want to say is that you can do at least that.
At least that, yes.
Not
So
exactly that.
yes, I can. What I want to say is I can at least take advantage of that. Right? And I just want to say that this is a non-obvious result. It would maybe take you 2 hours to solve it, but it's not something that you can just guess. Oh, majority will work, right? In fact, majority will not work. Why will it not work? Well, suppose that I will be using majority. Well, suppose you enter a sequence which is so let's say 1, 1, 0, 1, and then it starts to alternate, right? So well, okay, no, sorry, no, just 1, 0, 1, 0, right? This sequence. So I see 1. I'm going to go with 1. Oops, there is a 0. So I make a mistake. So now, okay, now it's how you break the ties. Suppose I break the ties towards zeros. I guess I'm switching back to 0, 1s instead of -1, 1. You get the idea, right? So anyway, you can construct examples where majority is not gonna do it.
If you randomize when majority is not determined, you randomize the
So even if I randomized with
sometimes the majority is not clear.
yes.
The ones and the negative ones.
That's right. So in fact, randomization is required. For all these results, randomization is required. And it has to do actually with the loss function being an indicator. If I had chosen a different loss function, which is, let's say, an absolute value or a square, it turns out that randomization is not necessary always. On our side, right? So it could be a completely deterministic result. For all sequences, I have a deterministic strategy, and it's a completely deterministic. But here you have to randomize because of the indicator loss. For all other loss functions, it can become. I hope to get there. I'll show you with linear loss, you don't have to randomize. Okay. So what is the phi in this example? Phi of the sequence y1 through yn is minimum of 1 over n, the frequency of yt plus 1, see from 1 to n, and okay, 1 minus, which is just the frequency of -1s, of course. Right? This is a function of the sequence. It measures the imbalance. Yep. If you give me a sequence which has a frequency 30, 70, the output of this function is 30. If you give me 90, 10, the output of this function is 10%. Yeah? So it just measures the imbalance of the sequence. So it turns out that I need to add 1 over square root of n here for reasons that will become clear in a second. And that's the same 1 over square root of n that it's the slack that I have. So big question. Does there exist a strategy? Now, what is a strategy? It's just a collection of qt hats. These are functions of the past, right? Each qt hat of y1 through yt minus 1, right? It only needs to depend on the prefix of the sequence. And it gives the output in minus 1, 1 for t from 1 to n. That's what I mean by a strategy. A strategy is how would you set your randomization? How would you set your bias? That is the strategy of the prediction, right? The predictor. Such that for any sequence y1 through yn, the expected 1 over n sum of y hat t not equal to yt is upper bounded by phi of y1 through yn. Right? This is the key question.
Didn't you just show that?
Yes, I didn't show you. I claimed it. Yeah. I claimed it. I showed it. I showed it for Bernoulli. Does there exist a strategy? I claim that there exists for this particular phi. Now, more generally, I can ask. I give you a phi, which collects the different behaviors, right, that I want to take advantage of. Does there exist a strategy that will guarantee that? No. So I stopped talking about IID there. It's arbitrary sequence, right? Plus minus 1 sequence, right? Now let me just say, I claimed here that there exists a strategy that will do it, that can take advantage of the imbalance, but the strategy is not obvious. I can point you to a paper by, let's say, David Blackwell at Berkeley, who was a famous statistician, wrote seminal papers in statistics, in game theory. And one of his last few papers in the mid-90s, which is called Minimax versus Bayes prediction, something close to that, he talks about these two setups where you assume that the sequence is Bernoulli, the strategy is obvious, you go with the majority, and you get a result that holds in high probability, or almost surely, over a draw from that distribution. And here you have the same result that holds for arbitrary sequences. The strategy is not obvious at all. And it's harder to derive. So there is this duality between what you can get in this IID world versus what you can get in this individual. Removing randomization.
The guesser from
That's right.
the provider to the guesser.
Exactly. You can think of this as a duality where instead of sequence being randomized, we are being randomized. We are randomized. But the fact that the reason we're randomized is really because of the loss function. It's not okay, that's
If you do
another.
If your loss function is +1 minus 1, it becomes like a zero-sum game, and then it's easier to
Yeah, so one way to actually guarantee the strategy here is to do backward induction and solve it as a dynamic program, and view it as a two-player game that you're playing against nature. That's one way to think about this. Okay, so I'm going a bit slower than I was hoping. In any case, I mean, I can do a whole course on this, on prediction of individual sequences. I'm just trying to give you a little bit of a sense of the results. Let me just put it in the context of Perceptron. If you think about Perceptron, it's essentially this setup, except we had side information xt. So what the only extra piece that we had there is you observe xt, then you make a prediction, whether it's cats or dogs, and then you observe the outcome. And the result was exactly this. The number of mistakes is bounded by some function of the both x's and the y's. And that function was the margin of that sequence and the radius of that sequence times 1 over n, right? So just to make this more concrete. Okay, so let's I want to understand what can I put here as a function phi. Wouldn't it be nice to understand what kind of phi can I put, right? So I told you I can take advantage of the imbalance. What else? Can I put in, you know, counts of every 3 bits? What's the fourth one? Can I put seasonality or whatever, right? So let me discuss this. Okay, so I have the statement that for any y1 through yn, expected average number of mistakes, indicator that y hat t is not equal to yt. I'm going to give a name to this object, and that is going to be mu of my algorithm A. So A stands for my choice of my strategy of y1 through yn, right? This is just a function of the sequence. So I would like to know if I can ensure that my number of mistakes is bounded by some other function of the sequence. Right? Correct? So now suppose that, well, I want this for any sequence, right? For every sequence y1 through yn, this holds. So if I have this result, then it better be the case that when I average over the 2 to the n sequences, mu of A of y1 through yn, that is upper bounded by the average right? So I'm summing over all the possible sequences. If this holds for any sequence, then this also holds. Correct? Now, what is this left-hand side? Well, I can write this as expectation over y1 through yn drawn uniformly at random from the space of all sequences. And that becomes expected mu A of y1 through yn. Okay, and here we have expected value of y1 through yn of phi of y1 through yn. Now I'm going to skip a step here and say, let me look at the expectation over sequences of this object. If I swap carefully the two expectations, the expectation over sequence, this is uniformly from the hypercube, and this expectation. And I have to do it carefully one by one, because here the expectation is, okay, well, let me skip that. So bottom line is, if I carefully swap this expectation with this expectation, then really what I'm asking is, can I predict a random sequence? This is expectation over my randomness, and this is expectation over the sequence. So if I swap them, I'm asking, can I predict a random sequence? And the answer is no. If my sequence is random, I cannot predict this. So this requires a little bit more than what I'm saying. It requires kind of a one by one swap of expectations. But the bottom line is that this is equal to 1/2. You cannot predict an arbitrary sequence drawn. You cannot predict a sequence drawn at random.
For any A, this is 1/2?
For any n and for any, yeah, so for any n, this is 1/2.
What is 1/2? The left side?
The left-hand side,
Regardless of your algorithm?
regardless of the algorithm. That's the beauty of this, is no matter which algorithm you choose, on average over all sequences, the number of mistakes that you're going to be making has to be equal to 1/2. So what's happening is, think of this as follows. You cannot predict you cannot predict all sequences better than 1/2 on average. But what you can do is you can tilt which sequences you prefer and try to do well on those sequences by tilting this kind of mistake bound to be smaller, and that has to be at the expense of the mistake bound going up on some other sequences, right? It's kind of a conservation of number of mistakes, right? It has to be, regardless of the algorithm, on average, it has to be 1/2, the average over all sequences. But what's interesting is that you can try to differentiate by having a particular algorithm. You can differentiate which sequences you prefer, but it has to be at the cost of losing on some other sequences, right? That's what you get from this conservation, right? Another thing that
Isn't this contradicting something? Like, because if the y's are Bernoulli, the 1/2 is the least you will do. So it's always more like it's
no. This is uniform from the. This is under the uniform from the hypercube. So this is Bernoulli 1/2, right? The equal probability Bernoulli. Right. But another thing that's coming out of this is that if our desired result is true, so if this is let's make a star. What we get is that the star implies, well, what is y1 through yn uniformly from the hypercube? You've seen this before. These are Rademacher random variables, right? So it's better be the case that expected over epsilon1 through epsilon n, I'm just renaming, I'm not doing anything else, phi of epsilon1 through epsilon n is at least 1/2. So if you were to have, if you were to engineer some function phi and hope that you can take advantage of things like imbalance like that or something else for all sequences, it better be the case that on average it's at least 1/2 over the hypercube.
Is this true for this kind of imbalance bias?
Yeah, so
Because of that slackness?
exactly. Right. So why is this true for this function? Well, let's look at the expected value of this function over coin flips. So what is the expected minimum of this? This is the frequency of +1s in a random sequence of coin flips, right? In a random sequence of Rademacher averages. And this is a frequency of -1s. Now, roughly, this frequency is 1/2 plus or minus 1 over square root of n, right? If you do unbiased coin flips, frequency of 1s and frequency of -1s, well, of course, they add up to 1, but they are around 1/2. And the minimum is always less than 1/2. The minimum is less than 1/2 by how much? About 1 over square root of n. That's why we add 1 over square root of n to lift it up to lift it above 1/2. Right. Now, a lemma due, let's attribute it to Tom Cover in information theory, says that the other direction also holds whenever phi is stable. So what is stable? Or let me say Lipschitz. Okay, let's keep it stable. It's just Lipschitz with respect to a coordinate. So we'll say that phi from ±1 to the n to -1, 1 is stable if phi of along every coordinate, if you change phi -1 bounded by 1 over n. Okay? So if this is the case, that the function is Lipschitz with respect to change of any coordinate, is 1 over n, then so this is like with respect to Hamming, right? If it's Lipschitz with respect to Hamming, then this direction can be reversed. In other words, expected phi being more than 1/2 guarantees existence of an algorithm. And the algorithm is computable, yes. And the algorithm is very simple, actually. So, since you asked, this direction says that the algorithm Q hat T can be evaluated by as n times expected over epsilon T epsilon n phi of y1 through y, t plus 1. T plus 1 through n, t minus 1, and then you put -1, and then, epsilon t plus 1, epsilon n, minus phi of y1 through y t minus 1 plus 1. Okay, I think I will have to check whether it's +1 here and -1 here. So yeah, I think it should be like this one. +1 here and then -1 here. and then epsilon t plus 1, epsilon n. That's the algorithm. What does the algorithm do? So first of all, I promised to you that the strategy has to be causal. It cannot it cannot peek into the future. So indeed, this is a function of y1 through yt minus 1. And the algorithm is the following. Think of phi as a potential function and check whether the potential is higher if you were to play +1 now versus to play -1 now if future is random. That's a random, think of this as a random play out, random rollout in game theory. So this is a, this is an algorithm. It's a simple algorithm.
Okay, so if there exists a phi like this, you can construct the algorithm.
So what you do is, if you've checked that expected phi is more than 1/2, then this algorithm gives you, and it's stable, then this algorithm gives you a number between -1 and 1. And that's the algorithm that will achieve this for an arbitrary sequence. It's a very powerful statement. And it's not obvious, so you have to do backward induction. If I had another half a lecture, I would prove it. Backward induction.
Does it say that phi is good? Like
Well, so you pick phi. You pick, so phi is your prior knowledge about what you want to capture in the sequences. You want to capture imbalance, that is the phi that you will take. If you want to capture something else, you take another phi. There is now a modular way to combine different phis. So for instance, if I have a bunch of different phis, I can create a meta phi, which is the minimum of those phis. Okay? That means that I will take advantage simultaneously of all of the phis. All I have to do is essentially to correct here a little bit in this 1/square root of n. Yes?
Is it saying that we have to randomize the majority of this tool, right?
It's like, well, right. So it's like a majority with randomization on top for this particular example. For this particular example, it becomes, look at the frequency,
And then
put one more +1 or -1, and then randomize. So add a bunch of hallucinated coin flips.
okay, but I mean the final algorithm, what would be that? Like we should compute the frequency and then pick +1 or -1 according to that frequency. And then
According to the frequency, which is shifted by a random amount.
of 1/n.
Well, whatever. So for that example, this will provide you a bunch of random average, right? Average of random variables.
Cancels.
It doesn't cancel, no, because it will not cancel, right? It will not cancel because it's inside of the min.
Then what would be the final frequency?
I mean, you can write it down. I mean, just you have this phi. A bunch of them are going to be epsilons, and now you take expectation. So it's like in game theory, it's called smooth fictitious play. You go for them. You look at who is the best now. You add random perturbation. That's the smoothing of the fictitious play, and then you go for the maximum. Thompson sampling is another version of this in Multern bandits. Or follow the perturbed leader is another version of this. Okay, Thompson sampling is a little bit, okay, very closely related, but slightly different.
So basically, it's like you're saying, what is the majority gonna look like if at time t is 1 or at time t is -1, and compare those?
Yeah.
Somehow, what do you expect the majority to be?
Yeah.
And what if you don't know?
If you don't know the horizon,
Yeah.
So there is a kind of a genetic way of dealing it. You get to n, if the game hasn't finished, if the prediction problem hasn't finished, you just double the horizon and proceed. So just trust me that there is a kind of a nice way to deal with that. And there are also modifications of this strategy. This is one strategy. There are some other ones which are inherently horizon independent. But the whole game here is actually to come up with potential functions. So think of this phi as a playing the role of a potential function, and you just compare, is it better for me to predict +1 or -1? And what's happening under the hood is that you have some potential, and if you've made a mistake, then you've learned something, and the potential dropped. And if you haven't made a mistake, the potential doesn't change, but you haven't made a mistake. So what you need is that the loss that you incur is upper bounded by the change in the potential. It's kind of a amortized analysis type of in computer science language. Okay, so the amazing thing is that there is this other direction. So let me give you the last kind of cherry on the cake. One way to define this function phi, if I think of this set of all sequences ±1 to the n, so that's a hypercube. And what I'm saying is I can choose any function on this hypercube, any function phi, that will encode my hope of which sequences I will encounter. Right? I just need to make sure that on average over this hypercube, this function is at least 1/2. And it's stable. Okay, so stability is really because of this indicator, because I need to give out, I need to compute a number between -1 and 1. That's why I need stability. I need this to be less than 1/n, so that's the reason. It's almost like it's a nuisance, the stability. It's not the. All right, so suppose that I do the following. I take a subset of the hypercube, call it F. And I say that, okay, I'm going to define phi y1 through yn as the Hamming distance, right? So from a point to the subset, a Hamming distance to the subset, a normalized. So this is normalized, right? So let me write this as a phi of the y vector, right? It's just the vertex of the hypercube. As a distance between y and the set F. And let me add some slack C. Allow myself slack C. What is the Hamming distance? That's a minimum 1/n, minimum over F in F, frequency of Fi not equal to Yi, right? This is the normalized Hamming distance between a vertex and the set. So again, I've chosen a subset of the hypercube, subset of vertices, and I've extended my phi to be, this is 0 on F, but I have to pay some C, so it's going to be C on this set F. And then as I go away from F, I go up by 1/n increments. 1/n increments. In particular, I satisfy the stability because of this. So if I flip one coordinate, then it's clear that I'm at most 1/n away. Yeah? So this let's call it a basic definition of phi, which is based on choosing a subset F. Okay, so now I need to make sure. So what I'm saying is I'm going to collect in phi sequences that I want to really predict well on those, right? This sequence is a collection of structures that I have that I want to take advantage of. Right?
Y is arbitrary. Like any
Yeah, so I have to define a sequence. I have to define a function on the whole hypercube for this, right? I have to provide you phi for as a function on the whole hypercube. So let me choose this one. You can define a different function, but that's one.
ignores most of the hypercube and only looks at f.
No, it just gives out a number, which is the normalized Hamming distance to f.
And f is
F is some set that I chose. So I choose f. F is a subset of the plus minus 1 to the n. Right. So let me, what do we need? We need the expected phi of epsilon 1 through epsilon n to be at least 1/2. So how can we guarantee it? So the claim is that I can guarantee it by understanding this c, how much I need to lift it up. So let's see how much. Well, let me rewrite this. This is expected min over f in f, f in f, 1 over n sum of indicator fi not equal to yi. This needs to be more than 1/2, or plus c. So c plus this. Okay, c doesn't depend on epsilon, so that comes out of the expectation. Oh, sorry, these are the epsilon y, epsilon I. Now I'm going to use the fact that the indicator of a not equal to b when a and b are plus minus 1. If a and b are plus minus 1, then the indicator can be written as 1 minus ab over 2. Let's just check that that's correct. If a is equal to b, then the product is plus 1, so I get 0. So that's correct. If there are different signs, a times b is minus 1, 1 minus minus 1 divided by 2 is plus 1, so that's the right relationship. I'm just going to plug this in. What do I get? I get that c plus expected over epsilon 1 through epsilon n min f in f 1 over n sum of 1 minus epsilon I fi over 2 is at least 1/2. So 1/2 comes out from the average and cancels with this 1/2. Then I have a minus epsilon I fi. If minus goes through the min becomes a max. So I get c minus expected max f in f. I think that's my phone. 1 over n epsilon I 1/2 epsilon I fi more than 0, correct? So I get that that c, so the smallest c that I need to add is expected max, or 1/2 expected max f in f 1 over n epsilon f, which are the Rademacher averages. How can this be? I thought we'll never see them again. Rademacher averages of c, of f. So up to scaling. So I guess what times 1/2. And this is quite remarkable because it says that well, how can I write that imbalanced example in terms of f? What is f for that imbalanced example? The min frequency of +1 and -1s. I want to write it as a min over a set f. Two vertices. One is all ones, the other one is all -1s, right? So in this example, f is +1 vector and -1 vector. I'll leave it as a homework for you to check that that is exactly. All I'm doing here is choosing two vertices, and that is my set f. These are my two preferred vertices. If they occur, I'll make almost no mistakes. In other words, if you just give me a sequence of all ones, I'll make 1 over square root of n fraction of mistakes, very small. If you start giving me something that's more imbalanced, I gradually have a guarantee that just depends on how far you are from either +1 or -1 vertex.
You mean if f is chosen this way?
If f is chosen that way, where you get back, how can I take advantage of imbalanced sequences? That is the choice for imbalanced sequences. Now I can put in other sequences. I can put in seasons. I can put whatever I want, right? This is genetic construction.
So if you knew that the number of bonds is going to be more than the number of zeros, then C would be 1 over n.
If I knew that, well, but then I wouldn't take that function. Yeah, but then that's not interesting. So Rademacher, what's Rademacher averages of 1 point? We've done this. This is 0, right? So there's nothing to do, right? I can just predict that sequence.
But then it gives a bound of.
It doesn't give a bound of 0. It gives a bound of how off you are from that function. Because I'm gonna predict that sequence, so the number of mistakes is exactly the fraction of times that my sequence, which is that sequence, is far away from your sequence, which is also my sequence.
You mean if f is +1 -1, you get 1 over square root n.
Yep.
From the Rademacher.
Exactly. So now you have all the machinery that we've developed before to encode all kinds of structures that you want. And how much do you pay for this? Well, exactly Rademacher averages of the function. Now, there's a much deeper connection here, which I don't have time. I need another 3 lectures. But there's a deep connection which essentially says if I introduce covariates, x's, right now it's not very interesting because there is no x's. But if I were to introduce x's into this problem, then I can develop a lot of similar results. And these would be not Rademacher averages, but what we call sequential Rademacher averages. The only thing that's different is that x can depend on epsilons as well. So here I would have something like 1 over n, sum of epsilon I. That's what I would have before, right? When you have a function class on the data. But now the data also depends on the epsilons. So the only thing that changes is that this becomes a function of epsilon I minus 1, but it's a martingale. This whole thing is a martingale difference. So a lot of the machinery can be extended to the sequential Rademacher averages. And what happens when you convert an online bound to an offline bound is you're saying, well, I've proved the result for martingales. I'm just going to assume it's IID. Of course, it still holds, and it gives me a strategy. So there's a whole world out there. This is just the tip of the iceberg. If you're interested, there's stuff to read that I can suggest. Right. I'll see you next week.